I can see that people still going up there. We have a respected researcher in the field of natural language processing here with us, Dr. Saatviga Sudhahar, and she's going to give us a talk about Knowledgegraph enhanced large language models. She has obtained her a doctoral degree, and then went ahead and also have a postdoctoral degree as well. She's right now a senior manager and also machine learning scientist at Healx, which is an AI-powered biotech company in Cambridge. Her specialties are in NLP, machine learning, knowledge graphs, and reasoning using deep learning as well. So as I said, her PhD is in engineering mathematics and AI from University of Bristol, and she's an author of over 20 peer-reviewed publications with over 500 citations and so on and so forth. She also mentor and works for HutchWorks in Sri Lanka and provide various mentorship for research projects and also incubator projects. She has been working with our department in the last couple of years in various projects, in various research projects, and very nice of her to agree to come and give us a talk today. And also she has helped us in the past with some of the lectures, delivering on graph neural network and advanced ML and etc. So very happy to have you here today physically, Saatviga, and over to you. Thank you for agreeing this time for us.
Right. Thank you very much for inviting me for this talk. So I hope I am audible in Zoom as well. Okay. 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 So today there's echoing. Should I okay. Now it should be fine. Yeah. Okay. So today's talk is going to be about Knowledgegraph enhanced large language models. So everybody's talking about large language models. So it's a big research field right now. But this talk is going to focus on a very specific topic in understanding how we can unify knowledge graphs and use them in large language models. So the outline of the talk today is about generally talking about LLMs, the problems that we face in LLMs, and how we can unify knowledge graphs and LLMs, what are knowledge graphs, and how we can incorporate knowledge graphs in LLM in different phases like pre-training, inference, and how we can use them effectively, and how this can help interpretability of these LLMs, because the LLMs are still black box models and lack interpretability. So how we can add this interpretation to these models, and talking about just listing out few representative applications and future directions in this research. So this is a very very active research right now. So people are still looking at how knowledge graphs can be incorporated into LLMs. So there's very few research that's happening, and I think in future you will see a lot more coming in this area. So as we know, language models is actually a probabilistic model that assigns a probability to every finite sequence in text, and there have been lots of models that we have seen in the past, like recurrent neural networks, and then there were convolutional approaches, and then there were this pre-trained language models like BERT, and there were different types. So in a broader sense, it all started with encoder-based models like BERT, Roberta, and then there was encoder-decoder models, which adds a decoder component as well to an LLM. So basically we encode sentences, learn an intermediate representation, and then a decoder is used to convert this to generate text, for example. So in NLP there are several tasks like summarization, translation, and encoder-decoder models got very popular in doing this. And then the latest are the GPT-X models, which are only decoder-based models. and without any fine tuning, they perform really well in downstream NLP tasks, including text generation. Now, why everybody is talking about LLMs? The promise is like one single model can solve many NLP tasks. Previously, pre-trained models required fine-tuning, but now with LLMs, there is lesser need for fine-tuning. There are several other approaches that people use now, like learning through prompts, in-context learning, lots of things. And LLMs are based on zero-shot learning. There's more and more data that's fed into it. There's more parameters leading to better performance. And it's quite
flexible because it can learn in an unsupervised manner, and you can give it like large amounts of text, and it's quite flexible. So recently, GPT 3.5 has a combination of several techniques, like it combines supervised learning and unsupervised learning, and also adds a reinforcement learning component. So people are now looking at how we can add reinforcement learning. So you provide some human input, and based on the correct question and answers, we add a reinforcement policy. Is that okay now? Yeah, okay. And so these are the latest advancements in LLMs right now. And this is like a roadmap showing what we are seeing right now with how it started with the encoder-based models and where we are right now up to the GPT-4, which is powered by ChatGPT. And most of these models are still closed source, and there are also open source alternatives coming up, like models released by Facebook like Llama and some of the alternatives of this. Now the problem is, now as we know, LLMs are making new waves because they are generalizable. You train it once and we can use it in many different tasks. We've seen great performance in NLP tasks like Q&A, machine translation, and text generation. And even right now we see a lot more LLMs trained with billions of parameters and solving complex problems like generating code, recommendation and all. But one problem that is there is a lack of factual knowledge in LLMs. So purely it's based on text, learns the context from the text, but it doesn't have an understanding of factual knowledge. So often this leads to something called hallucinations in LLMs, which means that they generate statements that are factually incorrect. So for example, an example of a hallucination is like when you ask a question like, when did Einstein discover gravity? The answer could be, Einstein discovered gravity in 1687. But the contradicting fact is that Isaac Newton formulated the gravitational theory, and it clearly shows that the answer is incorrect. So we can't really trust when it's showing something that's factually incorrect. And the other problem is inconsistency of the results. So for example, the same question, when you ask in different languages, there are examples where we see different answers. And there's lack of interpretability, and that's one of the main problems. And recently, to handle this problem, LLMs have used chain of thought reasoning, where you prompt the LLM with a chain of question and answers, and that helps it to arrive to a clear and clean answer compared to like a large chunk of text. But still, the reasoning is inconsistent. So it gives you an answer, but the reason for the answer is not correct. So the underlying cause is it doesn't know the supporting evidence because it doesn't know the facts. And this can be really problematic in very high stakes scenarios in specific domains, like, for example, medical diagnosis or legal judgment. So in the case of medical field, we can't expect to see wrong answers because people can ask very sensitive questions, and therefore there's a need to address this. So basically, I work in the drug discovery space, so I know how complicated it is. And when we predict a drug for a disease, we need to understand why the prediction was made. And the understanding behind this involves reasoning. Like it has to tell us, okay, this drug treats this disease because it's biologically relevant. So it needs to understand the biological concepts. And with generalized LLMs, we are not there yet. So there is a need for domain-specific models, like and that's also lacking. And domain-specific knowledge can come when we model facts into LLMs. So how can we unify these two things? So I work in Knowledgegraphs for the past few years, and I've used that to actually model data which is heterogeneous. So in a knowledge graph, it's basically a store or database of enormous facts of triples, which contains a head entity, a relation entity, and a tail entity. So I can explain a little bit more in detail. There are basically lots of knowledge graphs that you can access, like Wikidata, Iago, and NEL, which is called never-ending language learning, which learns facts from web. And knowledge graphs are actually renowned for their symbolic reasoning ability, because in a graph, it connects the concepts, and you can easily find paths between nodes in a graph, which can add to the reasoning ability. So knowledge graph is a separate research field, and there are several applications, and it's been used for reasoning as well. And people are now looking at building domain-specific knowledge graphs because it can effectively model it. And with knowledge graphs, it can also become dynamic. So you can model temporal information in the knowledge graph, and you can kind of add new information to the knowledge graph. You don't have to keep training it again and again. It can automatically learn representations of new nodes added to the graph. So there are several advantages, and it's a more structured approach to understanding and storing knowledge. So this figure here, it shows the pros and cons of knowledge graphs and LLMs. So with the LLMs, it's great, it's generalizable, it's having general knowledge, but the problems are, as I told, hallucination, black box approach, lacking domain-specific knowledge, and that's where the knowledge graph can feed in and provide interpretability of the results as well. There are also cons to knowledge graphs, like knowledge graphs are still incomplete. So there is still research going on completing knowledge graphs. So for example, there's a task called link prediction that tries to predict links between entities in a graph. And that's one problem. And it takes a lot of effort to build the knowledge graph, because you have to extract facts from text, make sure it's clear, not noisy, and you have to build the graph based on that. So it's less flexible. So whereas LLMs are more flexible. So there needs to be a unified approach. So how we could do that is what I'm going to show you. And this is just an explanation of how a knowledge graph looks. And you can see these graphs are heterogeneous, which means you can have different entity types. So this graph here is a political knowledge graph that shows relationships between entities, and these entities can be different types, like persons, locations, and you can think of different knowledge graphs like this, and they're being used in recommendation systems, the drug discovery space, fintech domain, legal domain, and many industry-specific use cases. And these are some other types of knowledge graphs that exist and people use. So there are encyclopedic knowledge graphs that model real world knowledge, like Wikipedia. Then there are common sense knowledge graphs, like modeling common concepts. Then there are domain specific graphs, like a medical knowledge graph that models entities and relationships in a biological domain. And there's also multimodal knowledge graph. So what I mean by multimodal is that it's not only just entities, it can be not only text, it can be images. So you can also model different types of entities in knowledge graphs. And recently, LLMs are also becoming multimodal because GPT-4 has the ability to understand images, audio, video, everything. And we can model the same information in knowledge graphs as well, but still they have not been incorporated in an LLM. So at which stages can we add these into LLMs is the pre-training stage in LLM is one space where you can input information from a knowledge graph. And at the inference stage, like for example, when we are trying to predict something, can we use a knowledge graph to improve the performance at that stage? Instead of pre-training, can we use this in inference? And then can we use the knowledge graph in interpretation phase to look at reasoning and how can we interpret the results? So I'm going to show like very few example models that are out there that's already doing this up to a certain extent. They have not scaled up to the LLMs yet, but they have been applied to models like BERT and Roberta. So I'm just going to show some models and how they actually get information from a knowledge graph and use them for LLM pre-training. One way is you can expose more knowledge entities in the pre-training objective. So there are models like Ernie and Luke that kind of enrich the inputs that go into the LLMs. So instead of just using token embeddings, learning textual context, you look at entities. So for example, I can show you a model which is called Ernie. On this left image, it shows how it encodes entities and text data. So given an input text, it takes the text sequence and also the entity sequence and get the embeddings for both and input them into LLMs. So we know how text is encoded in models like BERT and Roberta, but for entities, there are ways to learn entity embeddings in knowledge graphs. So we use graph neural networks to encode knowledge graphs and learn entity embeddings. So we can do that separately, pre-train a graph embedding for entities, and you extract that and input them in the LLM for pre-training. So that's one way, like how you can give the context of both a knowledge graph and text into LLM pre-training. So, and again, the rest of it is as usual, the usual way that
LLMs work. They have masked language modeling objectives, all these things to understand the input, and then that becomes a language model. But now the language model has an understanding of entities, not only just text, but entities from text and the relationships between entities. And another model, an example, I picked this example because it's quite interesting how a knowledge graph is incorporated here in the pre-training is you can add different encoders. So one encoder to encode text,
another encoder to encode the knowledge graph, and then there's a fusion module that actually concatenates these two and feeds them in the LLM. And if you look at this knowledge graph, there are interesting ways in which you can get a subgraph. So you don't have to actually incorporate the whole knowledge graph. So given a text sequence, it will look at corresponding entities in a knowledge graph, just get the subgraph of those entities, encode that information, and then input them in the LLM. And there are intelligent ways to do it, because even in the knowledge graph, we have techniques like attention, like we have in transformers, there is self-attention. Even in the graphs, we have something called graph attention, which tries to attend on the most important neighbors. And that helps to identify the context in a better way. And that can be then fed into the pre-training phase of an LLM. So the problems with, there are few problems in why when we use this in pre-training is that we cannot permit updates to the incorporated knowledge without retraining the model sometime, because when you add this information to pre-training, when there's an update, you have to retrain it. And the other problem is maybe they do not generalize very well during the inference stage, because when we do a prediction, we don't know what's the context it's using, whether it's using a text context or whether it's using a context from knowledge graph. We don't know that, and we can't quantify that. So that's one issue when we use this in pre-training. But still, it is an effective approach, like, because people are now thinking like how we can improve the knowledge that's already in LLM. We can think of adding these into the pre-training space. So this involves a little bit complex data processing, because you have to extract the subgraphs, you have to compute the graph embeddings, and then you have to input this to the model. Maybe a larger training time is required. So recently, what people are doing is to keep the knowledge space and text space separate, but you inject this knowledge only during the inference. So without pre-training the LLM, just leave the LLM alone, but then you get information from the knowledge graph externally and use them during inference. So we call this knowledge graph enhanced LLM inference. And there are several techniques to do that. You fine-tune LLMs on additional data. And there are few example models like KGLM. What it does is, given some input text, it would select some facts from the knowledge graph using the current context, and then it would generate sentences based on these retrieved facts, and that would then go to the LLMs as prompts. So you actually modify the prompts that go into the LLMs with facts from knowledge graph. So that's one way of using this in inference. And you can search through these models. There's another model called CagNet. It's again using like a fusing approach to actually get the schema graph and get the graph embedding and fuse them and use this in fine-tuning. One latest technique now, as I said before, is even in LLMs, there is a lot of research happening on prompt tuning. So given the prompts, the way you tune it has a massive impact on the results that is generated. So one problem with the LLMs is the nature that it cannot, it can only infer or produce knowledge up to certain time periods. So for example, if the training data was up to 2021, it doesn't have any knowledge after that. But to handle that is where we use fine-tuning or knowledge-based prompts. So we add additional data just to fine-tune it and then help the model to retrieve correct answers for a latest question. So if you ask a question about a 2023 event, sometimes it might not perform well because the main training data doesn't have that information. So that's why we use techniques like prompts, fine-tuning to help it understand like latest knowledge. So recently what's some research is focusing on is, in the prompt tuning phase, can we incorporate knowledge from knowledge graphs? And there is one model called KPPLM that does that. What it does is, it uses information extraction to extract facts from documents and creates knowledge graphs. And then it has a way to
convert them into natural language. So if you look at this picture here,
this is the context that's given to the model, and there is a topic entity that is identified from this context. And once it's there, what it does is it goes to a knowledge graph and pulls like the one hop and two hop relationships. So if it will query the knowledge graph for this entity, which is the COVID-19 vaccine, you can see this entity here, here, and it will pull the one hop and two hop neighbors and create this small subgraph. So this is a small subgraph here that's capturing the context of the entity COVID-19 vaccine. And it also has the other entities that you can see here. Some of them are topic entities, some of them are related entities, and you can see the different relationships between them. So once this is extracted, there are several chain prompting or converting them to natural language. So from this graph, you can convert them into chains. So these are separate prompts that can then go into the LLM to produce cleaner results. So that's one way of incorporating knowledge from the knowledge graph in LLMs. And a very recent approach is you can also think of it as retrieval augmented generation, which is also, it's been there for a long time, and it's been used for document retrieval. It's called RAG models. So what they do is they retrieve only relevant documents from the knowledge graph to generate a response. So right now, RAG models are also being considered to extract information from knowledge graphs and feed them to an LLM. So the problems is that we are seeing several models that's coming out, but they are not yet applied to the latest LLMs like GPT-X. So all of these are so far
tried with BERT or Roberta, and it's still working fine. And there's ongoing research looking into scaling this up to the biggest LLMs,
but we have not seen that yet, but I think it will come up in future. And then there comes a problem that is, as I was mentioning before, the interpretability of the answers that the LLMs is generating. So as I said before, knowledge graphs are most suited for structured reasoning. They can provide explainable paths. So as I said before, I work in the drug discovery space, and my main area of research is to understand reasoning for drug predictions. And I use knowledge graphs, but even that is a very difficult problem because understanding the context specific to that problem is very difficult. So, but knowledge graphs are capable of producing that reasoning. So the complexity is that we are not there yet with LLM. So there is a need to add KGs into LLMs. And one model that I could find that can do this up to a certain extent was something called QAGNN. So it combines, it has a way to combine graph neural networks and LLMs, and also use that for reasoning. So when an LLM produces an answer, we can go back to the knowledge graph and track the reasoning path for it. And there are other models that are coming up like LM Explainer and all. So the basic idea is you retrieve the reasoning path from the knowledge graph based on the generated content from these LLMs, and that becomes an explanation. So I think I'm just going to describe how interpretability can be achieved, and one of the examples of this interpretable LLMs is QAGNN. So what they basically do is, so now they have optimized this model for question and answering task, which is basically given a question, find the correct answer, get the correct answer. So what they do is, given a question and answer context, which is question and certain answers, there is a language model that encodes it, and then there is knowledge graph retrieval. So based on the concepts in the question and answer, you retrieve a knowledge graph. And then there is a joint graph that is created with language model encoding and also encoding from the graphs. So if you look at this graph, this is a joint graph that has the QA context, which is this node, and also the related entities in the QA context. So it's a way to model the context from language model and also a knowledge graph. And there are intelligent techniques like relevance scoring. So even with knowledge graphs, the subgraph generation, which is retrieving this graph from a huge knowledge graph, is a research problem, because sometimes you get noise. You just pull out a lot of information and that leads to noise. So there are ways to do scoring, so you get only very relevant entities in the knowledge graph, and language models are being used for that. So it's a very good way of combining LLM and knowledge graph and achieving this graph here. And for this Q&A task, what happens is, this goes then, once this is created, there is a graph neural network that is learned. So then this captures the final embedding from this graph neural network, captures both the context from LM and the knowledge graph, and then it goes to a multi-layer perceptron to predict the most probable answer. So that's the task that is mentioned here is a question and answering task. But the idea is that once you get the answer, you can go back and track the connections to that answer and the question from this knowledge graph. So it could be possible to generate paths from this graph that can provide some kind of reasoning. So there are lots of latest research work that's happening on how you generate explanations from graph neural networks. So this is one model that combines language models and knowledge graphs to achieve this. But still, it's still in a very early stage. We have to apply this to the latest LLMs, and we are not there yet, as I said before. Now, there are representative applications using LLMs and KGs, very limited at the moment. So as I said before, these are some of the applications and the different categories. So there are chatbots, there are coding assistants, there are recommendation tools using it. Lots of them are using LLMs, and some of them are just using knowledge graphs like Wikidata, OpenVG, and some other knowledge bases. And I think I showed you an example of Ernie, which is a model that combines LLMs and knowledge graphs to produce a language model that understands entities and relationships. So that is one model that has combined this. And Google Bard is said to actually incorporate Google's knowledge graph. So Google has built a large knowledge graph. As we know, it's used in Google search. So if you search something in Google, you can get not just the information about the entity, it will tell you the different connections. So that's achieved by the Google Knowledge Graph. But with LLMs, if you ask a question, you still get some context, but it's quite different from what you see in the Google search. So Bard is actually incorporating Google's Knowledge Graph into the responses it generates. So personally, what I found with Bard is the answers are a bit concise compared to ChatGPT. And one reason could be the use of knowledge graph in its knowledge base. So, and there could be more models coming out in future, but so far these are some of the applications using LLMs and KG, and also in the medical field, there is healthcare assistance that's coming up using LLMs and knowledge graphs. So for, as I said, domain-specific applications. This is just showing a general framework for how we could develop KG and LLMs models together. So we have input text and we have a knowledge graph. We can have different encoders for knowledge encoding and text encoding. The idea is a fusion module to combine this, and we could approach this problem in different phases of the LLM training. So through knowledge-guided pre-training, as I gave you some examples, knowledge-guided fine-tuning, and also knowledge-guided prompt tuning. So these are some of the resources I've just managed to put here. Recently, Neo4j is a knowledge graph initiative. They have like a huge GitHub repo and several tools to analyze knowledge graphs. And they are particularly focusing on combining knowledge graphs and LLMs and producing tools recently for this. So they really focus on this problem that I was talking about. And they're using even LLMs just as an interface. So the main query, what they do is, given a question, they use the knowledge graph to query something, but then the LLM is only used to produce a human readable answer. So the backbone will be the knowledge graph, but the LLM will be used as producing answers. So there are a few different ways we can use LLMs with KGs. Some of them I have explained now. Even LLMs are used to construct knowledge graphs. So LLMs are very good in actually finding missing information, missing links. It's even used to construct knowledge graphs. And Neo4j is one initiative looking into that. And there are several research approaches, and some of the models I've shown you today is some of the very latest models that look into this problem. And recently in the Knowledge Graph conference this year, there is a keynote talk on how important this is. And even some talks in EM-NLP last year had a few interesting talks on this. And this is a GitHub repository which has a lot of resources on how knowledge graphs and LLMs can be combined. So you could have a look at this as well. The conclusions is, given the impressive performance of LLMs on a variety of NLP tasks, we still see there is a shortfall in recalling correct factual knowledge and interpretability. And that's where there is active area of research in incorporating knowledge graphs in LLMs, and we need to follow a unified approach. So to make use of the pros of both LLMs and KGs. So some of the future directions in this area is still, this is in development. So we have to see more advances in future, but knowledge graphs can be used for hallucination detection in LLMs. So there are a few models that are trying to probe LLMs these days, like Llama, for example. What it does is, it gets some facts from a knowledge graph and tries to see if the LLM can generate that facts correctly. So you can use knowledge graphs for validating certain things from LLM, and it's called hallucination detection. It can even be used as a fact-checking model, so that can detect hallucinations across domains. Using knowledge graphs, it's also that there needs to be more research on how we can update this knowledge that's going into the knowledge graph. This is in a very early stage. It can be prone to noise, so this needs a lot of research as well. And right now, the research is only focusing on single modality of graphs and how we can use them in LLMs. But there are also multimodal knowledge graphs and temporal knowledge graphs, as I said, that can enable LLM to learn different entities and relationships over time. So there needs to be ways of actually modeling this in LLMs as well. And future work is also going to focus on domain-specific KGs and integrating them with LLMs, building custom LLMs so that you actually become very good in providing domain-specific knowledge. So these are some of the future directions in this area. So that comes to the end of the talk. Thank you very much. So I'm happy to take any questions.
On the Zoom as well. Zoom folks can type your questions in the chat. That's support the sound effect.
Okay, yeah.
We are ready to participate. Any question from the audience?
Hello, thank you for your presentation. So my question is regarding hallucinations. So hallucinations normally happen, could happen due to the temperature, right, of the softmax function. Basically, we make it more creative, then that's the reason why it became hallucinating. So isn't there like any research done on like controlling the temperature? I mean, we are trying to, I tried for Roberta base model where you can provide a mask. So when you type England is the, capital of England is, and then you give a mask, then it gives London, Manchester. But if you give Sri Lanka, capital of Sri Lanka is, then it gives like very low probabilities. So the reason is because one reason is because of the generative ability, right? So we are forcing it to be more creative. That's the reason why it's going towards like infactual things. So how do you make now introducing knowledge graph to strengthen the fact part is superb, but how do you like let the LLM decide whether the one which we are asking is something which is required by fact checked or not?
So that's where, so that's a very good question. But the thing is, so this is still in research. So as you said, like these hallucination issues can be improved by providing good prompts. And in-context learning is also about that. So there's also something called instruction tuning. So you can kind of tune the model to come up with correct answers. And hallucinations is also, so I think from my point of view, up to a certain extent you can make it better. But what I'm trying to say is still we are trying to modify a model that only understands textual context, right? So that's why we want to introduce the context from the knowledge graphs. But it is still not clear how it will be used in the inference stage. So that's why there are approaches that's looking at, like if you use them in the pre-training stage, it's very complex to understand whether it will be used in the inference stage or how it's used. But then if you use them at the inference stage by using like a retrieval augmented approach, so you can, I think that gives more chance to the model to understand the facts better. And one way of handling the hallucination is through this retrieval augmented generation with knowledge graphs. So in my opinion, I think up to a certain extent you can still do some modifications to improve this output, but then we need intelligent techniques during the inference phase or even the pre-training phase to make the model more robust to come up with the answers. But still this is an active area of research. So
Any other questions or any questions from the Zoom participants? Please mention in the chat. We haven't received anything yet. Anything else from the audience here?
In terms of encoding, so you talked about fusion models when we use LLMs and KGs. What are the main differences between encoding a KG and LLM? That part, yeah.
So the encoding that comes from a knowledge graph is actually a representation of entities. Like for text, you have textual embeddings that's generated by these pre-trained models like BERT or Roberta base. But for knowledge graph, how we get that embeddings is the knowledge graph that we are accessing is already pre-trained. So you already have embeddings for entities and relationships in the knowledge graph. So that's what we call graph representation learning. So you have an external knowledge graph, you pre-train it using several models. There are different models to do that. And that learns a representation for entities and even relationships in the graph. So when you concatenate, so at the input phase, you take the token embeddings, but for the corresponding entities, you can get the embeddings from the knowledge graph. So in the end, both are entities, both are vectors, and that can be easily fused in the fusion module. So it's externally learned. You can externally learn that embeddings for entities and incorporate them in the pre-training phase. Yeah.
Anything from the audience? Any other questions from the audience about? I mean, it can be related, not necessarily be specific to this. You can use this opportunity to learn from the experts for the students. So feel free to ask, if not exclusively in the topic that is being spoken here, any related questions also welcome.
You mentioned about fine-tuning the models. So like when it comes to like fine-tuning to a specific domain, let's say like a supermarket domain or like a banking domain or hospital domain, like, so is it better to like fine-tune the model with like, so like since like with limited data, or to use retrieval augmented generation, which might be better?
Yes. So that's exactly the problems I was talking about, and that's a good question. So when it comes to fine-tuning, I have worked in domain-specific models like fintech, legal. What I have tried in the past is constructing a supervised training set for that domain-specific data and use that to fine-tune a pre-trained model. So that's one way. But the problem is less amount of data. You have to put a lot of effort to create this data set. So I think the retrieval augmented generation is a much more efficient way compared to the fine-tuning with supervised data sets that we need to create. So with retrieval augmented generation, there's still a challenge, because when it comes to domain-specific knowledge, how can you retrieve that information effectively? So there are ways that now people are talking about vector databases and all that efficiently tries to retrieve this knowledge. So you need to put more effort on retrieving the correct contextual knowledge for that domain. And that is one problem we might face, but I think compared to fine-tuning, this is a much better approach, using a RAG model and using that with LLMs.
For the, I mean, we shared a feedback link for the talk as well as for the data search through the Zoom. Please use that to give us feedback about the talk, so that that helps the presenters. They always seek for such feedback, so we gather and accumulate and give. And kindly do let us know any other interesting topics that you want us to host from the data search. So that's also something we want you to sort of let us know what are the areas that you are looking for some added knowledge that we can help you with. Any other questions? Yes.
Yeah, this is regarding the knowledge graphs. Knowledge graphs, there is an entity, like there is a relationship. Normally the relationship is a verb, right?
It doesn't have to be a verb. So if you look at domain-specific knowledge graphs, it can be any type of relationships.
Right.
So if you look at the drug discovery space or a medical knowledge graph, it's the relationships between a disease and the gene. It's not verbs. Verbs is like common sense knowledge graph, or if you create a knowledge graph from like a general text, or say for example news data, you get verbs, but it can be any type of relation.
So the relationship, do you like predefine it already that these are the relationships which could be there? Right.
So there are techniques like, one is entity detection that detects the entities, and then there is relation extraction. So if you look at, there are different types of relations you can define and extract those. So there are different approaches, like even syntactic approaches to extract these relations. There are deep learning methods that train models to extract relations. So in a medical knowledge graph, we extract relations by training deep learning models. So we know like these are the relationship types, and even between the same entities we can have different relationship types. And so with these models we can extract these relationships and entities from text, and then we construct this knowledge graph.
Form a knowledge graph, so these entities when they are formed, they become massively sparse, right? Because
Sorry, I couldn't get
when the relationships are formed, those relationships can be massively sparse.
Sparse.
In the knowledge graph itself.
Okay.
So then like won't it again go, so imagine like where the example I said about England, London being the capital of England, that the language model was able to learn because it has come across it a lot of times. But same thing, if you have like a knowledge graph representing the same data, it will also come up properly because of the it has been occurring a lot of times. But for the problem where something about Sri Lanka being mentioned is very sparse in nature from the data itself. So knowledge graph, won't it also give the same response? Like I want to differentiate like how well or how
Yes.
can knowledge graph complement this weakness from the
yeah,
LLM?
so that's a good question. So with knowledge graphs, if there is sparse data, there are issues. So as you said, when the data is small or sparse about specific entities, we cannot extract all the relationships into a knowledge graph. But there are intelligent ways to model and learn representations in a knowledge graph, even with sparse data. So if you look at real world graphs, not every node is highly connected. Some nodes are having a high degree, some nodes will have a low degree, some nodes are not at all connected, say they are disconnected. So how you can learn an effective graph representation is based on these links. And in a knowledge graph, specifically in graph neural networks, there are approaches to solve this. So instead of just learning the entity representation for that single node, it will look at the neighbors features. So 1 hop, 2 hop, up to 3 hops. So you aggregate those features and get the embeddings for this entity. So you kind of, so that's one way it learns effective representations, because it's about the links between an entity and its neighborhood. So in that way, you can learn like rich contextual information.
There is not much questions from the online audience though.
No.
We have next lectures at 1:15. That's what the others left. No, we have the space here, but the students have to leave. Any other questions from the audience here? We can still have. Yes.
So like you mentioned about the rhetorical augmented generation. So like when fine tuning, we can like, if we have like lot of data, we can like restrict the LLM for a specific domain. But with RAG, like how can we like restrict for a specific domain? Like it will like provide factual data, and like so for like this restriction for a domain, like should we like do that in the prompt? Or
No, for restriction for a domain, you can access knowledge from domain-specific knowledge graphs or domain-specific documents. So the RAG model will only access the domain-specific information. So there is, people are now constructing this domain-specific knowledge. If you look at the fintech domain, you can create a fintech knowledge graph, and then you can try to match the textual context and the context from the graph by doing like a similarity search or something to retrieve the relevant documents from this domain and use it. So so it's like when it comes to domain specific, I think here I was talking about domain-specific knowledge graphs. So these knowledge graphs already have domain-specific knowledge in it, so from which you retrieve it.
So it's like this. So like if I want to like, so I want to talk in like in a banking domain. If I want to like build a chatbot, so like I have information about a specific bank. So then the Llama 2, let's say a Llama 2 model. So it is already pre-trained, like trained on like finance domain and banking domain, and like in a huge data set. So if I want to utilize that information as well as this information, how can I restrict the domain in that case?
So are you saying that both of them has finance domain related data, but what is the thing you want to restrict?
So I want to restrict the other things, like about like if a user comes and asks like what is the weather, like what's the weather today, and like so what's the best place to have a pizza or something, like random questions, like you should not answer those questions.
Okay, so I think it depends on the fine-tuning data set, right? So if it's domain-specific data, I don't know how the model automatically learns that this is a domain-specific thing. So I don't know if I answered your question, but I think with RAG models, it's automatically doing that implicitly to get that domain-specific data.
So actually, my question is like, so if I have a LLM that is like all pre-trained on different domains.
Okay.
So I don't want to get the answers from other domains, only from the finance domain.
So that's why you fine-tune it with finance data, right?
So I should fine-tune it.
Yes. Yes. So that fine-tuning is one approach. RAG is a different approach, but both are related to fine-tuning in one domain.
So like when it comes to RAG, like using like vector databases and stuff, is it?
Yeah, that is one approach, because now, for example, for a given context, like you can't keep generating, like when we do a similarity search, you can't keep generating the whole vectors every time. That's expensive. So there's something called vector database that computes these embeddings like before you start using it. So it's one big database which we call vector database, and that's used to do the semantic search. So using similarity, it will match the similar vectors there, and that helps to retrieve similar documents or similar knowledge.
Thank you.
We have one question from this audience that if they want to get into LLM to learn more about it, what could be the good starting point? Any insights into that that you want to advise them?
I think if you want to get into LLMs, first of all, you need to understand the basics. And I think Hugging Face has a very good tutorial on how, or not tutorial, a course on how pre-trained models work. So you need to understand the basics of language models. What are the basics tasks? What are the NLP tasks that it can solve? So I think starting with the Hugging Face course helps a lot. And I think there are more online resources that you can refer to, but Hugging Face is one of the starting points I would recommend. Yeah.
Thanks. I think that's warrant time. I was surprised that our audience stuck pretty much a reasonably large number until the Q&A, because usually they just fall out after the talk. But this was a decent success for us, like 50 plus audience and a good Q&A. So truly appreciate your effort, and thank you so much. I'm sure they have learned a bit, and our feedback form is getting collected, so I'll share with you. Thank you so much again for your time and a very, very useful presentation. You've compiled a lot of information together so that that's digestible for us. And there are a few people working on, Dr. Nisansa was online, and he's working with it. They work on, graph-based, graph neural networks a lot. He's one of our experts we have in that area, and there are a bunch of others working on chatbots and etc. So they would have learned a lot. So truly appreciate it. Thank you so much.
Thank you so much again for inviting.